Hello, I'm going to show you how to solve a linear second order ordinary differential equation with non-constant coefficients. Now, the differential equation in question is y double prime plus x times y prime plus y equal to 0. We'll call this equation 1. Now, I wanted to mention that this is linear, even though it has non-constant coefficients, because none of the coefficients are in terms of y squared, y cubed, or dy by dx, or d squared by dx. So this means because any kind of coefficient involving y or its derivatives therefore means that the equation is linear. Of course, there is at least one non-constant coefficient, but that is in terms of x, not y, so therefore it is linear. So we'll now go on and perhaps consider using the Wronskian to solve this differential equation. So our equation is of the form y double prime plus p of x times y prime plus q of x times y equal to 0. Now, as I said before, we're going to attempt to use the Wronskian in order to find at least, well, our first linearly independent solution. Now, in this particular case, the equation that I've stated, equation 1, is of the form y double prime plus p of x times y prime plus q of x times y equal to 0, where we clearly see that p of x is equal to x. And of course, the Wronskian is written in terms of w, meaning the Wronskian, which is equal to some constant, we've called it w0 here, w sub 0, times e to the minus the integral of p of x dx, where p of x is equal to x. So you will see here that we've got the Wronskian is, I've just put the Wronskian equal to some constant times e to the minus integral of x dx, and of course that integrates to give c e to the minus x squared over 2. So what we do now is we don't know for sure whether this Wronskian can actually be used as a linearly independent solution. So what we do is we suppose that y is equal to ce to the minus x squared over 2. And what we do is we differentiate it once to get the first derivative, which is this expression here for y prime. And then we differentiate for the second time to find y double prime, or y double dash as I often call it. And we get this expression here. And then we substitute those two expressions into the original equation 1. And so if we write out the first, or rather the second derivative, plus x times the first derivative plus the expression for y, we find that everything cancels and the expression is equal to 0. This means that y equals c1 e to the minus x squared over 2. I've just put another arbitrary constant in there. So y equals c1 e to the minus x squared over 2 is a linearly independent solution. So that is a particular solution that works because it equates the original equation to 0 as it should be. Now, we go back to the Wronskian again. Now, the Wronskian can be expressed as a matrix whereby we find the determinants of the matrix. Now, y1 and y2 are are both solutions. We already know y1. So we've got y1, that's one solution, but we don't know y2. Now, y1 prime and y2 prime are the derivatives of the first two solutions. Again, we don't know what y2 prime is because we don't know what y2 is. But we do know what y1 prime is. So if we go ahead and substitute in our first solution, c1 e to the minus x squared over 2, we differentiate it to get minus c1x e to the minus x2 over 2, but we leave the y2 and the y2 prime alone. And we equate that to our original Wronskian, which we know is of the form c2 e to the minus x2 over 2. This actually being also a first linearly independent solution to the original equation. But of course, it happens that the Wronskian is the same in this case. So I've just put that equal to another arbitrary constant, c2 e to the minus x squared over 2. Now, if we multiply out the determinants, so it's of the form y1 times y2 prime minus y2 times y1 prime, we get this on the left-hand side, and that is equal to c2 e to the minus x squared over 2 as shown on the previous slide. Now, this equation can be simplified, and what we get is dy2 over dx plus xy2, which is equal to c3. So that is our first order ordinary differential equation, and c3 here is equal to c2 over c1. So that is a much easier to solve first order ordinary differential equation, which we can find an integrating factor for. So with the integrating factor, it's similar to the coefficient that was in before, except this time it's e to the plus x squared over 2, not e to the minus x squared over 2. So our integrating factor is e to the x squared over 2. And if we multiply that throughout the first order ordinary differential equation, we have this expression here, which is e to the x squared over 2 dy2 by dx plus x e to the x squared over 2 y2, which is equal to c3 x squared over 2. Now, this is, well, the left-hand side is very easy to solve, and so you collect the terms together within the derivative part of the expression. So you get d by dx of y2 e to the x squared over 2, and that's in parentheses, which is equal to c3 e to the x squared over 2. Now, this is, apart from the fact that you can't really integrate the right-hand side, it is relatively easy to integrate. You would have to probably use error functions or some other kind of numerical methods to really go ahead and find, for example, a graphical solution to this equation. But what we've got here is y2 e to the x squared over 2, which is equal to c3 times the integral of e to the x squared over 2 dx plus a constant of integration, which I've called c4. Now, this can be simplified, and we get y2 is equal to c3 e to the minus x squared over 2 times the integral of e to the x squared over 2 plus c4 e to the minus x squared over 2. Now, it turns out that because the original equation 1 was a second order ordinary differential equation, this means that there are only two linearly independent solutions. Had it been a third order ordinary differential equation, there would have been three linearly independent solutions. So we would have had to go forward from here and find y3. But of course, we don't need to do that. We've got both of our linearly independent solutions, which are y1 and y2. the overall general solution is of the form y equals y1 plus y2, where y1 is equal to c1 e to the minus x squared over 2. So if we add our two linearly independent solutions together, we find that we have this general solution. Now, you will notice that in y2, there was already a term such as c4 e to the minus x squared over 2, as happened to be the case for y1. But of course, these tend to get combined together, and so you end up with the same sort of expression, but with a different constant, which I've called A here. And I've also called C3 a different constant B. It doesn't really matter what you call them, because if you put the initial conditions in, you will find what the actual values of A and B actually are. But this is the actual solution to the original equation 1. Of course, you would have to use probably error functions for this part here, the integral of e to the x squared over 2 or something like that, to find out what it looks like graphically, or to work out the solution for various points as x varies, and so on and so forth. So I hope that is I hope I've reasonably suitably explained how to solve a linear ordinary differential equation where you kind of have at least one variable coefficient. Not quite as straightforward as a more regular ordinary differential equation where the coefficient's constant, but nevertheless it is possible to solve some of these types of equations using these kind of methods. A little bit of intuition sometimes is necessary, so there are various techniques to use. You might not even always be able to use the Wronskian for these types of equations, but whether or not you use trial and error or the Wronskian or some other method is dependent on the original question and what is required of it. So I hope that's reasonably explanatory, and I'll see you in my next video. Okay, cheers then, bye.